Okay, let's do a review of what we've just been doing, just to make sure we're understanding this as best we can and more or less on the same page here. And then we're going to make a further observation as well with this whole idea of the relativity of simultaneity, and especially what Bob is observing here. So let's remind ourselves, this is really a combination of this last three video clips are really video clip 1 and then the just previous one where we were dealing with light pulses. So here's Alice's perspective on her spaceship. As far as she's concerned, she's not moving. She has the light pulse apparatus here. She shoots one light pulse that way, one light pulse that way. Her clocks are synchronized, so the light pulses both go off at the same time at TA equals 0 here, her time. En route, each light pulse is traveling with velocity c, and because they're equidistant from each other, the two clocks from the middle here, she sees the two light pulses hit her two clocks at exactly the same time, T, capital T sub A in each case. That's what her observation is. So as far as she's concerned, nothing's wrong, nothing weird going on or anything like that. So now let's look at Bob's perspective, and what we've done here is we have his frame of reference again, his lattice of clocks, all synchronized as far as he's concerned, and really three situations here. So we've taken the previous diagrams and tried to sort of like a little animation effect here, a stop motion animation, to say, okay, at T sub B equals 0, when all his clocks down here read 0, he observes the light pulses go off. At that instant right there, a little puff of smoke or something, and he would note what his clock says at that point. If it said 0, then it says all his clocks would be 0 at that point. And then, as the light pulses are in flight, remember the key thing is, even though Alice's spaceship is traveling with velocity v in that direction, that has no effect on the velocity of the light pulses. The velocity of the light pulses to Bob will be c, just as Alice saw the velocity of the light pulses to be c. They will not be c plus v or c minus v. And what that means is that because this rear clock on Alice's spaceship is moving toward this light pulse coming toward it, this light pulse will hit this rear clock before this light pulse can reach that clock. And of course, in real life, light is so fast and typically velocity is so small here, we don't notice this difference, but if you can get large enough velocities, this effect will come into play. Well, what do we know at this point? We know this light pulse just hit this clock. We know from Alice's observations, if we take a flash photo right at that point, we'll see that the clock reads T sub A, just like over here. That has to match at that instant in time and space. The light pulse hit that clock. Alice saw T sub A on her clock. What does Bob see on his clock? He sees TB1. Okay, so at that instant in time, at this clock right here, he'd take the flash photo as well, and they both could examine that photo. Her clock would read T sub A. His clock would read TB1, whatever that happened to be. And then moving on, note, of course, this one is still in transit. This light pulse is still in transit as far as Bob is concerned. And so at a later time, capital TB2 is when he sees the second light pulse, the rightward going light pulse, hit over there. And so the photograph would be taken, and it would show that Alice's clock read T sub A, just like she observed. But his clocks then would read, take a photo at that point, TB2. And so all his clocks here would read TB2, in particular this one as well, because they're all synchronized, of course, from his perspective. And what does this mean? Well, he read TB1 for this flash over here, TB2 at a later time for this flash, or the light pulse hitting the clock and triggering it there. That means this clock right here, if he took a photo right there and said, okay, I'm at TB2 here, what's this one? We know it's got to be a time greater than T sub A. So, get that? I mean, this is one of those things, we're constructing mental models here that are very different from our regular experience. We'd expect that Alice saw the two light pulse hits to be simultaneous on her clocks. Clearly Bob should observe the same thing, but because, again, the speed of light does not participate in the velocity of the spaceship, but is always c, no matter which observer we're talking about, Bob, Alice, or anybody else, you get this weirdness coming in. That Bob is, let's start with Alice. Alice is saying, what's the big deal? My clocks are synchronized. They hit exactly the same time. My clock's read T sub A. Everything's fine. Bob is saying, wait a minute here. It's my clocks that are synchronized, and clearly these photons did not hit at the same time. I read the first one at TB1, the second one at TB2, and in fact, when I recorded the second one at TB2, according to my lattice of clocks all synchronized, your rear clock, Alice, over here, was at a time greater than T sub A, because clearly it's later in time. So Bob sees Alice's clocks as unsynchronized. And you could reverse the analysis and look at it from Alice's perspective, looking at Bob's clocks. She also would see Bob's clocks unsynchronized, because otherwise you can't make sense of the situation. You know, the photographic evidence here does not lie, that when you take the photographs, it's got to be T sub A here, because that's what Alice sees. It's got to be T sub B1 for Bob at that point, and it's got to be T sub A over here for Alice, because that's what Alice sees, and yet it's TB2 for Bob. Okay, so that's just another review of what we were saying before, the relativity of simultaneity, that simultaneous events, clock synchronization, it's relative. You cannot absolutely synchronize clocks such that everyone agrees they are synchronized. If you're both stationary, if Bob and Alice were both stationary, they could agree they're synchronized. As soon as you put one of them in motion, especially at a velocity v that starts getting close to the speed of light, these effects start coming into play. So another way to say that really is absolute time cannot be defined. There is no way to define an absolute time scale or a way of measuring time such that both Alice and Bob would agree. Because Alice is saying, Bob, you messed up. Your clocks are not synchronized. Meanwhile, Bob is saying, no, it's not my problem. It's you, Alice. Your clocks aren't synchronized. And yet each individually have their clocks perfectly synchronized. Okay, so what's this? One more observation here that we're going to come back to later in the course. Let's look at Bob's perspective here. And he sees Alice flying by at velocity v in her spaceship. What does he see on her clocks here? Okay, let's look at this final situation here where he sees the photon, the second photon going to the right. He sees it triggering her clock. Photo is taken. Her clock reads T sub A, as Alice observes too. No disagreement there. They can't disagree over photographic evidence at the same location here, the same event. His clock reads TB2 at that point. He also, though, says, hey, my clock back here also reads TB2, and I just took this picture. But your clock is going to be at time t greater than T sub A. So the rear clock is going to be a higher value than the frontward facing clock, the front clock here, as Alice moves on. This is a principle, and we can state this as such. We'll use this a number of times. It's this. Leading clocks lag. Leading clocks lag. When you're talking about a situation where you have an observer, like Bob, and he's observing Alice's clocks going by, her lattice of clocks is flying by there, he will, if you pick any two clocks, say one here and a trailing clock over here, the leading clock will lag the trailing clock. This clock, T sub A, is behind this clock from Bob's perspective. Remember, all Bob's clocks are synchronized to him, so he could take a flash photo right here. His clock would read TB2. He'd take the flash photo at the same time as far as he's concerned. He'd read TB2 here. He'd see Alice's clock read T sub A, but he'd see this clock of Alice's reading a time greater than T sub A because this clock passed T sub A earlier when that photon hit, that light pulse hit. And so again, leading clocks lag. That if you have Alice flying by or whoever's flying by at a speed v that gets up close to the speed of light, we'll, in later video clips coming up here, we will actually look at how fast you have to be going for these effects to start becoming noticeable but for now we're just doing it qualitatively. And clearly the weird result here, takes a while to get our minds around this, is that, and this is why sometimes it's just useful to state it in a very succinct principle and just memorize that principle, leading clocks lag, so that Alice's clocks here, as far as Bob is concerned, the leading clock on the leading edge as she's moving that direction is going to be behind a clock, the trailing clock, wherever it might be. And later on in the course, we're actually going to do a calculation so we can figure out exactly how much does this clock lag this clock. And it's going to depend actually on the distance between them there. Okay, so a review of this first real aspect of weirdness we get, the relativity of simultaneity, the relativity of clock synchronization. Bob synchronizes his clocks, Alice synchronizes her clocks, but Bob thinks Alice has messed up. Alice thinks Bob has messed up in terms of his clock synchronization. And this idea that leading clocks lag. Not only do you have it's really a result of this whole idea that simultaneity is relative, synchronization is relative, absolute time cannot be defined, and that if you have a set of clocks moving by you at a high velocity, the clock that's leading will trail, in terms of its timekeeping, trail the clock back here, assuming that their clocks were synchronized in their own frame of reference, in Alice's frame of reference here. So just remember that principle, leading clocks lag.